Okay, what we need to do is to look at photovoltaic cells, or solar cells as they're known, and we're going to compare with a solar heating panel. So we know that the Earth receives about 1400 watts for every square meter. When you average that over the whole of the Earth during the day and during the night, it works out to be 340 watts per meter square. Now let's look at photovoltaic, or rather solar cells. They use solar energy and they convert this directly into electrical energy. They're at the moment only around 30% efficient, so we need a large area if we're going to produce much electricity. They're also kind of expensive to build, and it's been worked out that they're slightly more expensive than using diesel powered generators for its lifetime. Now compare with the solar heating panel. The solar energy is turned into thermal energy, not electrical energy, so it's basically solar energy into heat. These are cheap, but they're bulky, they need a lot of space, and they're usually put on people's roofs. They also need to be blackened to absorb more thermal energy. There is a confusion between solar heating panels, which are called solar panels, and photovoltaic cells, which are arranged in panels and so are sometimes called solar panels. So beware of the context of the question, whether it's talking about solar heating panels or solar cells. Usually solar panels means solar heating panels. Now photons arrive on the solar cell. We have two kinds of semiconductors. The N type basically produces an electron when the photons fall on it, and these electrons move up to the top, so the top becomes negative. That leaves a space, and these spaces are filled by electrons from the P semiconductor. So light photons arrive and give energy to emitted electrons, which move up to the contact at the top, so the top becomes negative. These negative electrons move up, and basically the holes move down, because these holes are replaced by other electrons that move up, so it makes the bottom contact positive. This generates a potential difference between the top and the bottom, and this is the voltage that's used to provide electricity. This is a nice graphic which demonstrates this. We have on the top left hand corner N-type semiconductor, a P-type semiconductor. The top plate becomes negative and the bottom will be positive. You can see what happens here. The energy comes in and the electrons move up to the top plate, which means that these electrons which move up have to be replaced by electrons beneath, so you get basically a flow of electrons upwards, and these come from the bottom plate, so effectively the bottom becomes less negative, or rather positive, and this provides a potential difference. These solar cells can be arranged in either parallel. Here you've got 4 cells each producing a small current, and then you add these currents together. The voltage will be the same, however. On the other hand, if you have them in series, you have the same current going through all 4 of them, but the voltages will add up. So this adds up to 2 volts. Or you can have a combination of the two. A problem for you to solve is how many people live in your house. Let's say you have an average power demand of 10 kilowatts. Let's say solar cells are 30% efficient. The power received over a year, over a day, the average day, is 340 watts per meter squared. How much area of solar panels do you need to satisfy the needs of your family?